Hi everyone, Vega here. In today's video we carry on with our Let's Talk series and we're going to do a second part to the Brightest Stars episode that we did 3 weeks ago now. Let's just have a quick recap of what happened in that episode. Of course, we looked through the brightest stars, flipping through Sirius. We went through Canopus, of Centauri, Arcturus, Vega, Capella, and I think we got up to Rigel in the end. So today's episode we're going to begin with what is rank 8 on the brightest stars in the sky list, and that is of course the wonderful star of Alpha Canis Minoris, or Procyon as it's probably best known to most of us. Procyon is an F-type star with an interesting designation there. You can see 1-5 to 5, which means if we look here on this table, the 1-5, or should I say 4 really, it's Roman numerals, isn't it, are classified as subgiants, and obviously the 5 is the main sequence stars. So without further ado, let's move straight on to Procyon. Procyon is of course the alpha star of Canis Minor, and a bit like Sirius is a binary star system with obviously the main star and a faint white dwarf. I always feel that Procyon is a bit of a understudy to the star of Sirius because they're very, very similar stars and in the same part of the sky. As we can see in this picture here, that's Sirius there, the brighter one, and Procyon is this one, the top left. I think that one there is the other star in Canis Minor, isn't it? Gamesa. This one's Procyon, and in many ways Procyon is very similar to Sirius in that it's also a binary system with a white dwarf, but its mass is slightly smaller than Sirius A, and its luminosity is slightly less as well. We see 6.93 as opposed to 25.4. We see Sirius is actually quite a lot brighter as an A class, of course, rather than F class. I always feel Procyon gets overlooked because of that a little bit. Colour index of 0.42, which is certainly pushing in towards the yellow part rather than the white. As we can see in this table here, the colour index, this Procyon with its 0.42 BV colour index is actually still, I mean, it says green there, doesn't it? That's quite interesting. I'm not really sure why it says green, but Procyon is the obvious example of that at 0.42. of a typical F-class star, which would be between 0.3 and 0.6. So not all yellow. I suppose that what they've done with the green there is because the Sun is a G-class star, isn't it, which tends to be called yellow dwarf. So for some reason they've disclassified Procyon and F-class stars as green. I can't explain that one myself, but interesting nonetheless. Obviously again the progenitor star of Procyon B, which is the white dwarf companion, was once upon a time a much bigger star than Procyon A, but again because it burnt its fuel quicker, being a larger star, probably pushing towards the A class, maybe even the B class. There is a video on that if you want to look at the progenitor stars of Sirius A and Sirius B and Procyon B. Take a look. What does it say here? It says the pair orbit each other with a period of 40.84 years. With quite an eccentric orbit, so it's a bit like separation as it says here. The average separation is 15 astronomical units, so a little less than the distance between Uranus and the Sun. It's quite an interesting system, isn't it? I always imagine looking out from a planet perhaps in orbit around Procyon A, and instead of seeing a planet like Uranus, you'd actually have quite a bright object. Should we check how bright Procyon B is from Procyon A? Let's have a look. So Procyon B has a tiny luminosity there, you can see, of 0.00049. We put that into our luminosity calculator, and we put in terms of kilometers, 15 astronomical units is approximately about 2.24 billion kilometers. So let's put that in. Which gives us an apparent magnitude of minus 12.68, which is approximately the brightness of the full moon. So quite an interesting star from that would be looking out from Procyon A. Quite an interesting system then. Let's go back to our list. Next one is the star of Achernar at 0.46 apparent magnitudes of variable stars we can see there. Alpha Eridanus Achernar is 139 light years away, and is one of those stars that we can't really see in the north. And it's a very odd star. It's one of those. I think is it the most oblate star? Yes, as of 2015, Achernar was the least spherical star known in the Milky Way. Now that's possibly because we don't know that many stars, but it would seem unusual that something so close would be the most spherical star we know about. It's a very odd star, and its equatorial diameter is 35% greater than its polar diameter. So a very egg-shaped star, and comparable to the dwarf planet of Haumea, which is quite interesting, isn't it? It also appears that Achernar has a companion. I'm not sure it's absolutely certain yet. I'm not going to go through that name there, but quite interesting. It says it's been identified as being at the same distance, sharing a common proper motion, as well as being estimated at the same age. So Achernar may actually be a binary system, but the projected separation of the two is slightly over 1 light year, so it's a very distant binary system. And in fact, it says even there that they would not be gravitationally bound, so perhaps not a binary system, but two very close companions, which is quite interesting again, isn't it? Another thing about Achernar is quite interesting is that it, along with Fomalhaut, they're a bit isolated. Fomalhaut and Achernar are the two first magnitude stars farthest from any stars. And finally, is the other thing about Achernar is Alpha Eridani, of course, is going to continue moving northwards. So if we can survive for 8,000 to 11,000 years, we might be able to see it as far north as Germany and southern England, which is quite interesting, isn't it? At number 10, this star doesn't really need any introduction, does it? The star of Alpha Orionis, or Betelgeuse, 640 light years away. An M designation, 1A supergiant. I won't spend too long on Betelgeuse because it's something that we've talked about a lot. A radius of 640 times that of our Sun, and if it were the centre of our solar system, its surface would lie beyond the asteroid belt. So you can imagine how big Betelgeuse is. Although, in terms of mass, I'm not saying 14 to 19 solar masses is anything small, but stars like Rigel, large blue class supergiants are actually more massive generally. It's just that Betelgeuse is in a late stage of its life. The future of Betelgeuse, it's thought that soon it could go supernova in the not too distant future. And it's actually interesting, this, isn't it? Betelgeuse is generally considered to be a single isolated star. It's not, in other words, it's not a binary. And also it's a runaway star that's not currently associated with any cluster or star forming region, and its birthplace is unclear, so it's a bit of an oddball, Betelgeuse. A lot of stars tend to follow roughly the same orbit around our galaxy, but perhaps something happened to Betelgeuse in its past that meant it speeded off in a completely different direction. I think the radial velocity of Betelgeuse, meaning whether it's coming towards the Sun or away, is actually quite high, and the plus designates that it's actually increasing in distance. So Betelgeuse over the next period of time is running away pretty quickly from the Sun, and also that means it will dim before it suddenly goes supernova. At some point, it says here, likely within 100,000 years. So Betelgeuse will slowly dim, very, very slowly of course, and then suddenly it will go out with a bang before it disappears completely. And again, with these large stars, we don't really know what will be left. It could be a black hole, it could be a neutron star. A lot depends on the gravitational forces within the star and the star's core size. It's not a guaranteed black hole which you might expect. Even some of the most massive stars are all not necessarily guaranteed to become black holes. It's a bit unpredictable. So it could become a neutron star, is basically what I'm saying. I won't speak too much more on Betelgeuse because it's quite a famous star anyway. At number 11, we have Hadar. The star of Beta Centauri is probably most famously known. Hadar's a very, very complicated system. As it says here, triple star system. I don't know what you folks know it as, but I think most people perhaps know it better as Beta Centauri. I certainly learned as a youngster as that name, but it was recently acquired the name of Hadar. Again, a southern hemisphere star, So we can see here in this diagram that is Centaurus, and obviously Alpha Centauri, which is Alpha Centauri, and here's Beta, which is quite... I've not actually been in the southern hemisphere, so I've not seen it, but it must be very impressive to see these two really bright stars, and then obviously pointing across towards the Crux constellation with Crux there at the top. And then if we point downwards from Crux here through Acro, that's actually almost directly to the South Pole. So I've always wanted to see the Southern Cross, and obviously Centaurus, the constellation, as well. The stars of Beta Centauri, so we've got a very large giant B-class giant star, and at B1 it's one of the hotter types. It's almost into the O class there. Beta Centauri designated AB is another one with the same designation. And then Beta Centauri B is a main sequence B-class star this time, but also a very hot one, almost again into the O class of stars. So it consists of a pair of stars, Beta Centauri AA and AB, that have a period of 357 days. So not too dissimilar from where our Earth is around the Sun. Although it says here the pair were calculated being separated by a mean distance of 4 astronomical units. That's actually they're quite far apart, so obviously they're spinning around each other a lot quicker, around a common centre of gravity. Whereas it doesn't actually seem to say how far the Beta Centauri B star is, although I'm sure in the video itself, I've actually done a video on Hadar, you could have a look in that. It's quite interesting here, isn't it? It says Beta Centauri B is a B1 dwarf with a apparent magnitude of 4, so even without the two major stars, it would still be visible with the naked eye, but nowhere near as impressive. But I find that quite bizarre, how you can actually call a B-class star a dwarf. Let's have a look at them. Does it actually say the mass? Yeah, so we've got a 4.61 solar mass star being classed as a dwarf. Well, I don't know what that makes our sun. I suppose compared to most giant stars it probably is a dwarf, but certainly a very, very strong, powerful one if ever there was one. So that's Beta Centauri or Hadar. The next star we move to is number 12 with a apparent magnitude of 0.76, is the Eagle star of Altair. Altair is obviously a very fast rotating star, and another one of those stars that's not really spherical. As we can see, this is quite an interesting graphic, isn't it? If we compare it to the Sun, Altair is obviously a lot larger, but also more egg-like, if you like, in shape. White star. Altair is a BV colour index of 0.22, so it's not totally white. There's probably some elements of yellow in the Altair star, with a spectral type of A7VN, broad nebulous absorption due to spinning. Altair, of course, is another star on its own, and after the star of Sirius, I think Altair is the closest A-class star to us, at the distance of 16.73 light years. And yeah, the other interesting thing about Altair is it's one of a few stars that's actually been photographed. That we're looking at is actually a real image of Altair. It's incredible, isn't it, that something so far away can actually be... The disk can still be photographed, but that's what Altair really does look like, interestingly. And it's interesting, isn't it, that through the years there's other stars that are very close in line of sight of Altair, all of these ones here that we can see, but none of them are considered to be binary stars much further away than Altair, but in the same line of sight from us. There's a little graphic there of it. I like that one actually. I might save that for a future video. A very nice image there of Altair. So let's move on to the next one in our list. Is Acrux. Acrux Alpha Crucis, of course, again is a very, very, very complicated system. If you're really interested in Acrux, again, I'd advise you to watch the video, because as I say, I'm talking a bit off the top of my head here from memory, and there's just so much intricacies and minutiae about the Acrux system that I'm no doubt going to make an error in what I say. It's quite interesting here, isn't it, that the apparent magnitude is similar to Altair at 0.76, but it's really coming from two stars, of which both are substantially dimmer but making the star brighter itself as one unit. Let's see if we can find a diagram of Acro, because it's very difficult to explain what goes on in the Acro system, and I have done it before. Let's see if I can find one. Here we are. This is more like the system. So you can see that we have a binary. One of the major stars is also, I think it's a spectroscopic binary, with another large B-class star, then one on its own, then I think is a large. Again, I'd advise you to watch the video because it's quite a difficult system to get your head around. Acro, it's one of the most complicated I've ever come across. So you've got A1 and A2, which are the larger stars, and then we have an M dwarf, quite a large, powerful M dwarf. We have a G-type unknown temperature, which is very similar to our Sun actually, there at 0.97 solar masses. And then we have another main sequence B-class star, and then a giant B-class star and another unknown, completely unknown designation B-class main sequence star. So one of the most complicated systems we know of. There are some incredible photos of Acro though. Let's see if we can bring them up. Here's Acro as seen by Cassini, so you can see the main pairing there, and there is another one of the Acro system. This is seen by Cassini. There's another picture, I think, with the rings of Saturn. Yeah, there it is. So you can see Acro there again, the double pairing of the larger stars with, I think, one of the larger B main sequence stars there, and that is actually one of the rings of Saturn there. So very photogenic star, even although it's very difficult to make videos about Acro because it's such a complicated system. It occurs to me as well, I'm not actually explaining where it is. So in this Southern Cross we have 4 major stars. We've got Acro, Mimosa, I think it's Ima, and then Acro is the one right at the bottom. So definitely not a star that's very easy to see at all, unless you're in the southern hemisphere. That's Acro. You might see that I'm struggling a bit more on these lists than I was the first lot, because the stars are just more complicated, the systems. Let's perhaps do a couple more. Aldebaran, at last, a more simple system to explain. So we've got 0.86 apparent magnitude. Aldebaran is still very bright. Alpha Tauri, of course, 65 light years. And a K-class giant star. Aldebaran in some ways is like Arcturus as well, is actually an analogue of our Sun in the future. As we can see there, the mass isn't all that much more than the Sun at 1.16, but the radius 45, leading to a huge luminosity of 439. It's a late stage star, age 6.4 billion years old, which actually does suggest that Aldebaran is, I'm not sure it says what the progenitor star of Aldebaran was, but I'd say it was probably pushing into the F class. If it at 6.4 billion years old, our Sun wouldn't actually have gone red giant by then, or orange giant in Aldebaran's case, so probably an F class star as the progenitor star of what we see now as Aldebaran. Another star in the beautiful winter hexagon, and also very closely related to the Pleiades cluster, not in terms of actually being gravitationally bound because they're quite distant from each other, but they're very close in the sky, which I always found quite an interesting part of the sky to look at, of Taurus, which of course the Pleiades is within the boundaries of Taurus. It says the star spins slowly and takes 520 days to complete a rotation, so that is very slowly, isn't it? I think the Sun is around 20 something days, so a very slowly spinning star. And also Aldebaran B, there's a planet of a Jupiter size. Let's have a look at some of the details of Aldebaran B. Mass 5.8 Jovian masses, so quite a large super Jupiter there, and also not far from the star in terms of being well, obviously it's going to be very difficult to be habitable around a star like Aldebaran, but 45% farther out than the Earth, which of course with Aldebaran being expanded means that it's got a very high temperature there of around 1500 Kelvin. But again, it's quite interesting because although Aldebaran is no longer a main sequence star, for a long period of time it was, of course, and this Jupiter-like planet, if it stayed in the same place, would have had a equilibrium temperature comparable to that of the Earth, so any of the moons around the world could perhaps have been habitable. So, and given that Aldebaran is slightly older than, well, quite a lot older than our Sun, a few billion years older, any life that has had formed in the Aldebaran system has had plenty of time to evolve. Possibilities of life on Aldebaran, I'd say fair, rather than zero. Intelligent life I'm talking about, but if there is, it's certainly had to have migrated out from the Jupiter-like exoplanet. So let's just go back to have a look at the list. I think I've run over time again. They're just so interesting, aren't they, these stars, that we can talk about them forever. So we've actually done a few stars there, 7 stars, and probably we're going to need at least another episode, maybe even 2. Antares coming up, Spica, which is a star that I never spent much time looking at, but the videos on Spica tend to do really well, so it's obviously a star that people like talking about. Just bearing in mind what we've been looking through, Procyon starting at plus 34 and leaving at Aldebaran, so we're almost, once we leave Aldebaran, we're almost pushing into 1 apparent magnitude of plus 1, still slightly under with Antares and Spica there, aren't we, but Pollux certainly quite a lot dimmer than that. And again, most of these stars are southern hemisphere stars, so perhaps, I don't know what it's like to live in the southern hemisphere. I always thought it must feel a little bit isolated maybe, but certainly not in terms of celestial things to look at. In fact, of the ones we've looked at, we've only got Aldebaran, Altair, Betelgeuse, Procyon, Capella, Vega and Arcturus that are actually in the northern hemisphere. All the other ones are in the south. So in fact, perhaps any of you in the comments that have seen both the southern hemisphere skies and the northern hemisphere skies, let me know what the difference is and which you think is more impressive. But certainly in terms of brightest stars, I think the southern hemisphere wins, doesn't it? So looking at this list, so that'll leave you with something to think about before our next episode. I think we'll wrap it up there. Again, don't forget to like and subscribe if you've not done already. Check back in 2 or 3 weeks if not, perhaps we'll put a third part of this video out if it's successful. Obviously take really good care of yourselves, look after yourselves well as always, and I'll see you on the next one.